Okay, continue. Example. And if f of x equals to x to the power of 2 over 3 for all real x, okay, and that means our domain minus infinity comma plus infinity open interval, okay, and if you try to sketch this function, okay, you will obtain approximately like that curve, okay, and what can we say about it? Okay, and we say that this point is endpoint, which is plus infinity, and of course we can say this is plus infinity, okay, and the L and M are plus infinity, so we can find any, or we can find some points on this open interval which is less than L and M values, okay, and of course you can find lots of points like that, and according to the theorem, an absolute minimum exists. Okay, so critical point del y over del x is equal to 2 over 3, okay, x to the minus 1 over 3, okay, and this point is 0, okay, and we can say the limit, okay, x approaches to 0 from left hand side, del y over del x, it equals to minus infinity, okay, because of the slope will be negative, okay, and the limit x approaches to 0 from right hand side, del y over del x, it equals to plus infinity. So there is a cusp, okay, and the singular point at x equals 0, also y equals 0, okay. Another example. F of x equals x cubed plus 3x plus 1, okay, and so that we can say this for x element of minus 1 comma plus 1 closed interval, okay, and for critical points derivation of y function, which is 3x squared plus 3, and it is equal to 3 times x squared plus 1, and it's not equal to 0 for any real x, because of we know that x squared does not equal to minus 1. X element of real. We know that. So critical point, none. And we know that del y over del x larger than 0, so we can say this function is increasing function. And so no singular points for this function. And for endpoint, we can say the f of minus 1 equals to minus 3, and f of plus 1 it equals to plus 5. And sketch it. Plus 1, minus 1, and minus 3, and the plus 5. This point is, which is endpoint, and it is the local and absolute maximum. And also this is local and absolute minimum. Example, if y equals to f of x, it equals to x squared, for all real x, and we know that the critical point, we can find it by the derivation, and which is the 2x equals to 0, so x equals to 0, y equals to 0. This point is critical point, and we know that x squared and this point is local and absolute minimum. Now let's continue the section 4 0.3 and the 4.4, which is related with the sketching graph of a function, okay, and I will give these two topics together, okay, and maybe it will be easier to understand, okay, for you, okay, and 3 and 4 sections, okay, and subsections, sketching graph of functions, and firstly let's understand the concavity and inflections. Okay. We have some points, okay, and okay, like that, and this is f of x function, x, y, okay, and the intervals a, b, c, and d, okay, and my friends, on AB intervals, as you see, our curve is increasing, so we can say if there is an increasing interval, this is plus sign, okay, and we can say f prime of x is larger than 0, okay, its sign is positive, so that, and look at this interval, as you see, it is increasing, okay, and we can say f prime of x is less than 0 here, so the minus sign is valid, okay, and for this interval again, our function's curve is, please attention, our function curve is increasing, so that f prime of x is larger than 0, so here is plus sign, okay, and these are the sign of f prime, okay. And then let's talk about this example, very popular example about this topic, and our function is x cubed function, okay, and what can we say about this? And we know that the y prime, it equals to 3x squared, okay, and we know that 3x squared is, okay, larger than 0, right? So for all real x, okay, and we can say y is always increasing on the domain of f function, okay. Please remember its graph, okay. Oops. Duplicating the pen, so sometimes very hard to sketch, okay. This is y equals to x cubed function, okay, and please attention, as you see, this function is always increasing, on the interval of this function, as you see. Okay, and let me write another example. Okay, and if y equals to minus x cube, so y prime equals to minus 3x square, and we know that it's less than 0 for all real x, and we can say y is always decreasing. Okay, let me define the concavity. Definition: the graph of a differentiable function is concave down on an interval where the slope y prime decreases it is concave down, concave up on an interval where the slope y prime increases. Okay. Example: x cube, okay, and we know that the y prime, which is equal to 3x square, is larger than 0, and we said that the y is increasing, okay, and we know that the y2 prime it equals to 6x, okay, and it is larger than 0. Okay, we know that the 0 less than x is less than plus infinity, and we know that 6x is less than 0 when minus infinity less than x is less than 0. So what can we say about this interval? Okay, and we can say for here, okay, and it is increasing and the concave up, okay, and as you see, increasing and the concave up, and then here decreasing and the concave down, okay, and let's remember the functions graph, okay, my friends. This is y equals to x cube function, okay, look at for this interval, function is always increasing, but okay, your curve, okay, here, which is less than 0, it is concave down, okay, and for this interval, when x is larger than 0, that means the positive x values, okay, as you see, your concavity is up, okay, as you see. And we can say the graph of y equals to f of x is concave down on an interval where y2 prime is less than 0, okay, and the graph of y f of x is concave up on an interval where y2 prime is larger than 0, okay, I mean that. So let me write it again, okay, to understand it. The graph of f of x is concave down, as you see, on an interval where y2 prime is less than 0, and the graph of f of x is concave up on an interval where y2 prime is larger than 0. Okay. And continue with the another example. If y equals to f of x, which is equal to x square function, okay, and we can say y prime equals to 2x, okay, and we know that when x is less than 0, okay, and y prime is less than 0, okay, so y is decreasing, okay, and again when x is larger than 0, we know that y prime is larger than 0, so y is increasing, we know that. And what about y2 prime? It is equal to 2, so it is larger than 0, okay. What can we say about it? We can say it is for all real x, okay, so the graph, okay, is always concave up, okay, and that's enough, I think. And the points of inflection topic, let's continue with them. A point on the graph of a differentiable function where the concavity changes is called a point of inflection. At the point of inflection, on the graph of a twice differentiable function y prime equals 0 and it is positive on one side and negative on the other side. Okay, and talk about example. And y equals to sine of x. Okay, and this is sine of x graph. Okay, okay, assume that this is sine of x graph. Okay, and we know that okay, and this point is pi over 2. This is 3 pi over 2. Okay, and this point is 5 pi over 2, and this point is minus pi over 2. Okay, and we know that this point is okay pi, this is 2 pi, this is 3 pi, this is minus pi. Okay, and please look at for this intervals. Okay, for here we can say it is the concave up, as you see, up, and here concave down. Okay, and here is concave up again, and here is concave down. Okay, and all these points, okay, and we can say that here and the y2 prime is, okay, y2 prime is larger than 0. Here is y2 prime is less than 0, y2 prime is larger than 0, and y2 prime is less than 0. Okay, and please look at for these points. Okay, and all these points are, we know that y2 prime equals to 0, so these are inflection points. Okay, inflection points mean that concavity, okay, will be changed. Okay, so as you see, concave up here, and this point concave down. So at this points, okay, inflection point. Okay, don't forget it. And at the inflection point, always y2 prime equals to 0. Okay, after that, please continue with the example. If f of x equals to x to the power of 4, okay, and what can we say? We can say y prime equals to 4x cube, okay, and it is equal to 0, so x equals to 0. We know that x equals to 0 is critical point, and it is, this point is local and absolute minimum point. Okay, and if y2 prime, okay, equals to 12x squared, okay, and it is larger than 0, and we know that it is concave up, okay, for all real x, okay, and y2 prime equals to 0. We know that at x equals 0, of course, and what can we say? Is it an inflection point, okay, or not? Okay, firstly, we must look the functions, okay, at the x equals 0, okay. My friends, please attention, okay. As you see, yes, here is a candidate, okay, inflection point because of the y prime equals to 0 at x equals to 0, okay. But as you see, here is concave up and here is concave up. Concavity didn't change, so we can say no inflection point at x equals 0. Okay, that's important.